6.6, analyzing arguments with quantifiers. We've got a universal quantifier and an existential quantifier. It's basically two new symbols. Looks like a upside down capital A and a backwards capital E. But the first one, this one, is basically talking about all, each, every, and none. The existential is basically talking about some. So, for instance, all babies are illogical. All babies are illogical. Now, that's going to be this symbol, and you're thinking about if it's a baby, then it's illogical. We kind of can combine those two ideas, but the result is going to mess with your head a little bit. I think it's just going to look kind of confusing because we're going to install a variable x. So that says for all x bracket b of x arrow I of x. That's how we're going to have to write all babies are illogical. And so what the variable does is that the variable allows us to have different babies. For example, if I plugged in M, that might be like Madison is a baby. So X is a variable that could mean something else, okay? If I said I, running out of room here, if I said I, K, that might mean Kevin is illogical. And so I know that looks kind of confusing there with that symbol and the extra variables and stuff like that, but it's just trying to get us to where we can say universally all babies are illogical. So then some is this backwards E looking symbol. If it's a baby, then it's illogical. We're going to have this. There's some X, there's some instance where it's a baby and it's illogical. So those are your two kind of forms. When it says all, you're going to use the arrow. When it says some, you're going to use the and symbol like that. Then we need to negate it. If we have to negate those quantified statements, I guess what you need to notice is when we negate this one, it turns into this one. There's more to it, and we'll get to it, but when you negate this one, it turns into this one. Essentially, negation changes this symbol into this symbol. So I probably need to give you an example here. You've got some space right there. Let's write this down. I'm going to have two lines of text here. So start with this one. If I took that statement and I said, well, let's take that statement and let's negate it. We're trying to negate that universal statement. This is going to be equivalent to this. There's some Hi, thank you. Like so. Then we can even go further because from chapter 6.3, from 6.3, we can distribute this negation in here. But when that happens, it turns us into this statement. So there's two different things. If we negate this red statement for all x such that all babies are illogical or whatever, you can either go to the black, or if you need to go to the green, you can do both of them. Now, I didn't give you enough room. Maybe if we write smaller. There's another one if we want to negate this statement. Your sum turns to all. But then again, we learned in 6.3 how to distribute that, or how to negate that. Like so. Get all of that down, because to me that's the hardest part of the lesson. But now that you have it, you're just going to use it. If they give you this part, then use it. If they give you this part, then use it. And that's what example 1 is about. It says write the statement symbolically, then write the negation and translate back to words. Some Texans eat quiche. So we know the sum is going to be this symbol. And let's let T stand for Texans and Q stand for quiche. So when we use that sum, it's going to be T of X and Q of X. Look like that. That's the statement. Write the statement symbolically. Some Texans eat quiche. But then we've got to negate it. So when we negate that, check your equivalency. And I'm going to go from the from here to here. This is what I'm going to do. So when I negate that, it turns into all. Oh, and I forgot my little negation right there. And so you can think about this as, if you're a Texan, then you don't eat quiche. But when we combine that with this, we're going to say something like all Texans don't eat quiche. All Texans don't eat quiche. But that's a little bit clunky when you think about the English language. There might be a better way of saying it. Instead of that, all Texans don't eat quiche, it might be more efficient to say no Texans eat quiche. Okay, let's try part B. Some Texans do not eat quiche. Once you see a few of these, you're doing the same thing over and over again. Some you're Texan and you do not eat quiche. We need to negate that. We've got it symbolically. Now we need to negate it. And I'm going to use that equivalency that we wrote on the previous page to change this to all. And we're going to negate the negation of q of x. So it turns out that just kind of wipes itself out. And if you've got not q, then that's just going to turn into q right there. So there's the negation. And so what does that say? It says all Texans eat quiche. Part C, no Texans eat quiche. No Texans eat quiche. Well, that's kind of what I have right here, right? We don't have a symbol for no, but we're talking about all Texans don't eat quiche. So, really that's what that says. All Texans don't eat quiche. So we're saying all Texans, if you're a Texan, then you don't eat quiche, is the statement. That right there says no Texans eat quiche. We got to negate that. And when we negate it, it turns the all into a sum. And then it's also going to change your arrow into an and symbol, and it's going to negate the negation here. Not q is going to be q. Look like that. You can read it as some people are Texans and eat quiche, I guess, but the most concise way to say it would be some Texans eat quiche. All right, number 2, represent the argument symbolically and then tell me if the argument is valid. All elephants have wrinkles. Start with that part. That's the easy part. That means all. Elephants have wrinkles. When you have all, it's going to be an arrow. If there's an elephant, it has wrinkles. Looks like that. That says all elephants have wrinkles. Babar is an elephant. So all that is an example of an elephant. So I'm going to say EB, like that. That says Babar is an elephant. And then the conclusion, therefore, Babar has wrinkles. Look like that. That's the symbolic representation of these words. And if you look at it, it kind of looks like one of our properties that we've learned previous in this chapter. It looks like the one where we land on E and we get to slide to W. See how we have an E, we have Babar as an elephant, so we can land on this E of X and we slide to W of X. It looks like that one, which was called modus ponens. Now, it's not the same thing as modus ponens because that didn't have the universal quantifier in it, but it sure looks like modus ponens. And so I suspect this argument is going to be valid. Here's how we're going to show that. We're going to show it this time. Instead of doing logic, instead of doing a truth table, we're actually going to draw a Venn diagram. Kind of weird, but it's effective. Since we start with all elephants have wrinkles, what we're going to do is we're going to say, okay, there are things with wrinkles. And since we know all elephants have wrinkles, we can put the elephants circle completely inside the things with wrinkles circle. And since we know that Babar is an elephant, we can put Babar right there. We know all elephants have wrinkles. We know Babar is an elephant. And just by looking at our picture, we can see that Babar is also inside the wrinkles circle. Therefore, Babar has wrinkles. This is valid. And that picture right there is all it takes to show that this is valid. Number 3, same question. All frogs are slimy. If it's a frog, then it's slimy. That's how I think of it in my head. Kermit is not slimy. So I would say not S of K. Therefore, Kermit is not a frog. Like that. Now this one's a little bit harder to recognize, but when I see this, that one looks like modus tollens. And that was another way to show that an argument is valid. So I suspect that this one is valid, okay? But how I'm going to show it is with that same kind of picture. So I'm going to draw a circle. And since it says all frogs are slimy, I'm going to start with slimy things. And I know all frogs are slimy, so we can put the frogs circle completely within the things that are slimy circle. And so at this point, it says Kermit is not slimy. When I know Kermit is not slimy, then that means Kermit has to go out here. And we can see from the picture, if Kermit's not slimy and he's outside of that circle, he's also outside of the frog's circle. So we should be able to deduce that Kermit is not a frog. This is valid. We can see that Kermit can't be a frog. Questions? Number 4, same thing. All well-run businesses generate profits. So this is your symbol for all. If it's well-run, then it generates profits. Look like this. Monsters, Inc. generates profits. So I can do something like that. P of M, Monsters, Inc. generates profits. Therefore, Monsters, Inc. is a well-run business. Look like that. Now, this one's not the same as the last one. I'm looking here and here. Remember on the last one, there was a negation somewhere. There's not this negation here. This looks like one of those fallacies. This looks like fallacy of, there were 2 of them. There's fallacy of the inverse and fallacy of the converse. Converse means switch them. That's what this one looks like. Looks like fallacy of the converse. So I suspect this is not going to be valid. I suspect this argument is invalid. Let's draw that picture. All well-run businesses generate profits. So all well-run businesses generate profits. Things that generate profits. Well-run businesses. All well-run businesses generate profits. Looks like that. And then we know Monsters, Inc. generates profits. But like what we don't know is we don't know if it's here or here. We know the Monsters, Inc. generates profits, but it doesn't give me specific enough information to know whether it's inside or outside that well-run business. We don't know. Okay, we don't know at this point if Monsters Inc. is a well-run business or not because it might be here and it might be here. This is invalid. Number 5, all squirrels eat nuts. All those who eat nuts are healthy. All who are healthy avoid cigarettes. I'm going to use A for avoid cigarettes here. Therefore, all squirrels avoid cigarettes. Does that one look like any of them to you? To me, that looks like the one where if you land on S, you get to slide to H, but if you land on H, you get to slide. No, that's an N, sorry. If you land on S, you get to slide to N, but if you land on N, you get to slide to H, but if you land on H, you get to slide to A. So that means if I land to S, I get to slide all the way to A. That feels like that transitive one. It looks like the transitive one. Transitive, that's a V. Transitivity. I think that was called hypothetical syllogism, but transitive property looks like that. So I suspect that that's valid. All squirrels eat nuts. So I'm going to abbreviate there. All squirrels eat nuts, but all those who eat nuts are healthy. All those who eat nuts are healthy, but all those who are healthy avoid cigarettes. Therefore, all squirrels avoid cigarettes. And we can see that the squirrel's circle must be completely inside the avoid cigarettes circle. This is valid. Last one. Should say number 6, I guess. Same question. Some U.S. presidents have won the popular vote. Some. Let's go PX and VX. George W. Bush was president of the U.S. P of G. Therefore, George W. Bush won the popular vote. Okay. Doesn't really feel like any of my properties here. So let's just see. It says some U.S. presidents have won the popular vote. Some of them. So this is a little bit different picture this time. So you've got U.S. presidents, but only some of them have won the popular vote. That's a picture of some U.S. presidents that have won the popular vote. It says George W. Bush was president, but we don't know if he's here or here. According to this information, we don't know if all they're telling me is that he was a president. We don't know if he won the popular vote or not. It's invalid. Not a valid argument.